All right, good morning, everybody. Welcome back. Good to see everyone again. I hope that you had a lovely Tuesday and that you watched all three parts of the lecture at your leisure. If that meant 8:30 for you, great. If it meant a little later, then also fine. Um, for what it's worth, on Tuesday morning, I got up at 3:30 in the morning. Uh, so I didn't get a nice lie-in on Tuesday morning. Actually, just got up way earlier. So I was happy to sleep in all the way until 7 a.m. this morning. By comparison, it was a luxury. Okay. The last lecture was pre-recorded. It was done a little bit differently. Felt like it probably went a little fast. It might have been a little harder to follow. I apologize for that. If you do have questions, I want to talk about them. I want to answer them. I want to make sure we're all up to speed. And yeah, we can all be glad that that's not what class is like every day. So I have a warm-up question for you here. We have a bipartite graph. Can we find a subgraph that's a cycle with 3 vertices on it? So let's just review what some of these things mean. So a bipartite graph, that means I've got these two parts, A and B. And I don't know what's happening between the two parts, but none of the vertices inside of the parts have edges between them. So we know a complete bipartite graph has all of the edges possible, but I might just have some of them. So there we go. There's a bipartite graph. And what I want to know is if we zoom in on this graph, if we pick 3 vertices, can we find a C3, which also happens to be a K3, but it's a triangle, right? 3 vertices all connected to each other. What do we think? Okay. Got an answer from chat. No. Cyclic movement is never complete. Let's see, is the rest of chat convinced? All right, this is what we mean, by the way, when we say a proof. We need an answer that we can all agree on. So if we have an answer but we're not sure, then it's not a proof yet. So we've got some agreement. So the agreeers, how do you explain your argument to those who aren't sure yet? How do we think about these things? How about this? What type of proof technique do we have that could help us prove this? We don't have a ton of proof techniques for graphs yet, but we've talked about induction proofs, we've talked about proofs by contradiction, proofs by contrapositive. What might be helpful here? Okay, good. I like the intuition. Something with contradiction. So we've got a couple of ideas now that we've crowdsourced. Something about we can't complete the cycle, and maybe we can use contradiction to show that. So indeed, the answer is no. So let's make that a theorem. A bipartite graph cannot have a C3 subgraph. Okay, and let's prove that. So if we're going to do this by contradiction, let's start with assume for sake of contradiction. Now we need to assume something. Well, the thing that we want to contradict is that there is a C3 subgraph. We're going to assume that there is a C3 subgraph and then get a false. Get a contradiction somewhere. So that G is a bipartite graph with, let's say, parts A and B, and that V1, V2, and V3 are vertices of G, that form a C3. Okay, right? This is how we set up our contradiction proofs. We say that you can't have a C3 subgraph, so we assume that you can. And in particular, we're assuming we know exactly where it is. Okay, so let's think about this. My vertex V1 has to live somewhere. Has to either be an A or B. And A and B are just labels, so I can just assume that it's an A. Because if it was actually in B, I'll just swap the labels. Let's put V1 here. So I can assume, sometimes we say without loss of generality. This just means that if this wasn't the case, I could swap the names, and then it is the case that V1 is an A. Okay, so this is V1. What do I know about V2 and V3? Since V1 is connected to V2 and V3, and I'm in a bipartite graph. Yeah, good. Since V1 is adjacent to V2, and I'm in a bipartite graph, V2 has to be in B. Because V1 is adjacent to V2. V2 has to be in B. That's how bipartite graphs work. Similarly, V3 also has to be in B, because V3 is also adjacent to V1. Okay? So now I have V1 over here, V2 and V3 over here. How do we bring it home? What's the contradiction? What goes terribly wrong? There we go. Very nice. V2 and V3 are both in B. They're supposed to be adjacent, but that would put an edge inside B. So, two ways of saying this. We got both back to back, which is fantastic. Either one of these finishes the proof. We can either say V2 is not adjacent to V3 because they're both in B. That's a contradiction because they're supposed to be adjacent. Or we can say they are adjacent, but that's not possible in a bipartite graph. You can come with the contradiction from either way. I'm going to choose the first one just because it was suggested first. Since V2 and V3 are both in B, they are not adjacent. Contradicting that V1, V2, V3 form a C3. There we go. That's the hard part of the proof. Now we just write one more sentence that wraps it up nicely. Therefore, no such C3 subgraph can exist. Okay. How are we doing? How do we feel about that? Let's go through that again. What do I mean by C3? This is good. This is a good question. So in class on Tuesday, we talked about some different standard graphs. I think that this was in part 2. So we labeled the cycles Cn, where when you had n vertices all connected in a big cycle. So labeling n vertices. So C5 is a pentagon. C6, hexagon. C4 is a square, and C3 is a triangle. That's okay. This is good. This is a good review. So how did we do this problem? We got asked this question, and it seemed like if we tried to put a triangle in the bipartite graph, we couldn't wrap it around. We couldn't finish it in the right way. And since we tried to do it but couldn't, that led us to say, okay, let's try a proof by contradiction. So we set up our proof by contradiction by saying, assume that there was a triangle, that it was already there. And if it was already there, we can say it's this vertex, and this vertex. We know them. And then we saw what went wrong when that happened. Well, what went wrong was I have this one vertex somewhere. It's adjacent to 2 other vertices. All of the adjacencies have to go across the way from A to B, which meant my 2 other vertices were both in B, and that's where the problem lay, because they're supposed to be connected, but they can't be connected if they're both in the same part. So, reasonable next question. What about C4 subgraph? Can we fit a C4 subgraph into a bipartite graph? So a C4 cycle with 4 vertices. We got a square going on. Okay. No for the same reason. Let's take a look. A and B. What happens if I try and squeeze a square in here? Well, I need some vertex V1 And V1 is going to be adjacent to V2 and then V4. Right, if I label them like this. So I got V2 and V4, and these edges have to exist. Okay, but I'm not in trouble right away, because V2 and V4, they're not adjacent to each other. Right? There's no edge here, but that's okay, because there doesn't have to be an edge here. But we know V2 has to be adjacent to V3. So where does V3 have to live? V3, good. V3 has to now be back in A. So now V2 can come back across, and V4 can come back across. Okay. Well, it kind of looks like we did it, except are these two graphs the same? V1, V2, V3, V4. We have a no. Why not? What's different between these two? Number of edges. Let's see. Let's count up the edges. So I've got 1, 2, 3, 4. Here I've got 1, and then I've got to be careful. Remember, crossings are allowed. There's no vertex here. So this is still just 2, and then 3, and then 4. So remember, one of the important things about graphs, this was from part 1 of Tuesday's lecture, the picture doesn't matter. All that matters are the vertices and the edges. These are two pictures, but if we look at their vertex set, V is the same in both cases. V1, V2, V3, V4. The edge set has an edge from V1 to V2, an edge from V2 to V3, an edge from V3 to V4, and an edge from V4 to V1. And when I say from and to, that's not entirely accurate, because these are not directed graphs. So just an edge between V1 and V2, V2 and V3, V3 and V4, V4 and V1. I even wrote V1 and V4 instead of V4 and V1 because this is an edge, it's a set, and order doesn't matter. V1, V4 is the same as V4, V1. Remember from set theory. So this is the graph, V comma E. These are pictures, but the picture is not the graph. This is the graph. So now, are these two graphs the same? Yeah. Even though I drew them differently, even though they have different pictures, they are the same graph. There's a V, there's an E, they line up, they agree. They are the same sets of things. They have the same vertices, they have the same edges. All right, now, I'm going to throw a twist your way. Here's another picture. Is this the same graph as up here? Are they also spanning subgraphs of each other? Yes. That is true. They are spanning subgraphs of each other because they're the same graph. Every graph is a spanning subgraph of itself. Okay, good. So, graphs are not pictures. This is a graph. This is a graph. They're not the same graph. This one has an edge between V1 and V4. This one has no edge between V1 and V4. When I list out the set of edges here, they have the same vertex set. But when I list out the edge set, some of the edges are in common. They both have V1, V2. And they both have V3, V4. But this graph has V2, V4 and V3, V1. And those were not edges in this graph. Okay. Remember, graphs are all about relationships. One of the common examples we use to think about graphs, especially really big graphs, is the Facebook graph. Everybody on Facebook is a vertex, and you put an edge between two people if they're friends on Facebook. These are different networks of friends. Right? Here, V1 and V3 are not friends. Here they are. That means that these are different. Okay, but really, I mean, how different are they really? If I draw this picture and I draw this picture, yes, they are different, but they have the same picture. Having the same picture, oops, you can't see that. Having the same picture should count for something, right? And so we have a name for graphs like this. Graphs that have the same picture but are not the same graph, well, even if they are the same graph, are called isomorphic. So if this is G and this is H, we say G and H are isomorphic. Written G, H. So what's our symbol for this? It's not that they're equal, because they're not exactly the same. They're just kind of equal. So we have equal with this little squiggle on top. Sometimes you only see one line. Or G, squiggle equal. Either way, I don't have a strong opinion. I don't actually remember what we do in documents and theorems. Let me pull it up real quick. Make sure I'm consistent. We might not use either. Yeah, we don't use either. That's what I thought. Okay, so either one works. So what does it mean to be isomorphic? What it means to be isomorphic is that there's a way to shuffle around the labels to make them the same graph. So in this case, if V1 stays V1 and V2 stays V2, but I relabel V4 into V3, and I relabel V3 into V4, then I would have the same picture. What this means is I have this original group of vertices, V1, V2, V3, V4, and this new group of vertices that confusingly have the same names, And I can just do a swaparoo. I say this one goes here, and this one goes here, and this one goes here, and this one goes here. And once I do that, then they will be the same graph. That's what we mean by isomorphic. We can shuffle around labels to get the same graph. And that's really important because technically, let me go back to my V1, V2, V3, V4. Technically, these are different graphs. Because these ones I called V vertices, and these ones I called U vertices. But with isomorphism, if the graphs are isomorphic, all I'm saying is there is a way to turn the V's into U's. So I'll use a couple words that we'll talk about later in the semester. What I'm doing is I'm creating a bijection between the vertices. I'm creating a function that is one-to-one and onto. We'll talk about all those words later. But all you need to do right now is think of it as a swapping of the vertices, a relabeling of the vertices, reorganizing. Okay, those are our isomorphic graphs. Okay, let's keep going. Lots of stuff to talk about today. If I look at a graph, they have all these different connections that we can follow, right? So let's look at one of our sample graphs from class on Tuesday. Okay. One of the things we can do on graphs is think about sort of wandering around. So let me give these all labels. A, B, C, D, E, F, G, H, I, and J. And maybe I start at C, and then I wander over to E, and then I'll go up to G. And at each step, I'm just following an edge. Maybe I'll go back to E, up to D, down to B, over to A, go back to B. And so this wandering process is really useful when talking about graphs, and we call this a walk. So a walk in a graph G is a sequence alternating between vertices and edges incident to those vertices with no vertex repeated in a row. So what do these look like? They look like V0, and then edge 1, and then V1, and then edge 2, and then V2, and then E3, and then V3, all the way up to EK, VK. And the trick is I can't have two vertices back to back that are the same. I can't say I'm at vertex C, I'm taking this edge. Oh, but wait, I made it back to C. If I take the edge, I have to end up on the other side of that edge. So here I would take V0 is C, and then I take this edge, and then V1 is E, and then I take this edge, that edge, and then V2 is G, and then I take this edge, and then V3 is F, and I continue along my walk. And a walk is closed if V0 is equal to Vk, and otherwise it is open. Okay. So this was an open walk, but I could make it a closed walk by taking one more edge from B to C, and now it's a closed walk. Okay. Questions about what I mean by a walk? I'm going to build on top of this definition, so I want to make sure we're all good. So we've got lots of special types of walks. Lots of different walks that mean different things. It's going to be really important to be able to keep these definitions straight. So the walk is the most general thing. A trail is a walk where we don't repeat an edge. So no edge comes up more than once. So you might find yourself back at the same vertex you started from, but then you've got to go somewhere else. You can't retrace an edge. Okay, so that's an example of a trail. If we want to be even more restrictive, a path is a walk without a repeated vertex. So here, I can't come back to that same vertex. I just have to keep going to a new vertex every time. Okay, explain this with an example. Yeah, I mean, this is an example of a trail. This is an example of a path. Not sure I completely understand. And we talked about path graphs yesterday, or Tuesday rather. So a path graph was just a graph that looked like this, and now you can see why we call it that. That's exactly the path we take here. Would the first one still be a trail if it ended at the box? Yes. This is still a trail. We have not repeated any edges. That's okay. There aren't any closed walks. There can be closed walks. There cannot be closed paths. A closed path would have to start and end at the same vertex, but paths are not allowed to have the same vertex show up more than once. There can be a closed trail. That's okay. Right, a closed trail doesn't have to go around forever. It can start and stop at the same vertex. And that's okay. But we can't have a closed path. Next important question, is every path a trail? If it is the case that we're not repeating vertices, is it true that we're also not repeating edges? Yes. This is good. If you can't repeat a vertex, then there's no way to take an edge again. Because in order to take this edge from this vertex to this vertex, I'd have to get back to this vertex or back to this vertex. I'd have to get back to one of the two sides and do it again. But I'm not allowed to ever return to either vertex. And I can't go back. That's maybe an important thing for my path, right? I can't take the same edge back right away because then I'm repeating this first vertex again. You can in a walk. Can't in a trail, but you can in a walk. Can't in a path. Like I said, gonna have to keep all these straight. All right, we have a few more. So a trail has no repeated edge. A path has no repeated vertex. A circuit is just a closed trail. So think about this like a race car track. You can go around in a circle. It's a very dangerous race car track because you can take the same edge. You can go through the same point, go through the same vertex. Just can't take the same edge again. So this is like a destruction derby where I'm going through that same point multiple times. Or a Mario Kart track. Here I have a circuit, right? If I label these A, B, C, D, E, F, G, then A, B, C, D, E, F, G, A is a circuit. Start and end at the same place. Even though A shows up more than once. Oh, sorry, I missed one in there. A, B, C, D, A, E. A, B, C, D, A, E, F, G, A is a circuit. There we go. All right, and last but not least is a cycle. So if I don't repeat a vertex, except for the start and end spot, then I get a cycle. So a cycle is a circuit where only the first / last vertex is repeated. And only V0 is equal to Vk. So the only time I see the same vertex again is when I'm back at the start. Or alternatively, it's a path with an edge between the first and last vertices. So these look like our cycle graphs that we were talking about earlier. Just a nice closed cycle. And they don't always have to be drawn in a nice, pretty pentagon shape or n-gon shape. They can cross over each other as long as there's no vertices there. We just have A, then B, then C, then D, then E, then back to A. And A is the only one that's repeated. Okay, so walk, trail, path, circuit, cycle. Walk, trail, path, circuit, cycle. Those are our 5 concepts here. The walk is the most general one. It's just walking along the graph, vertex to edge to vertex to edge to vertex to edge. If you don't repeat edges, you have a trail. If you don't repeat vertices, you have a path. If you end up back where you started without repeating edges, that's a circuit. If you end up back where you started and you never repeated vertices, except for that one time where you end up back where you started, that's a cycle. Okay, let's pause there for a couple minutes. Give everybody a second to digest that, get caught up in writing. We'll come back 9:15, just about 2 minutes. See everybody then. Yeah. So we have that one. This was before that. And then walks were before that. No problem. Okay. I got 9:15. Let's gather back together. Refocus. So, here's a fun game. I'm going to draw you a graph. And your goal is going to be to find. So there's a graph. And I'm going to give you a labeling so we can talk about it. It's maybe not the most sensible labeling in the world, but I want you to find a circuit. Let's recall what that means. A circuit is going to be a closed walk where I don't repeat edges. So a circuit that uses every single edge in this graph. I want to start and end in the same place, and I want to hit every edge. The way you may know this game is I want to draw this whole shape without backtracking or lifting up my pencil, or in this case, my Sharpie marker. How do I do it? What sequence of vertices lets me cover every edge? All right, we got one. Let's give it a shot. F, G, A, B, C, D, E, H, F. Let's see if that works. F, G, A, B, C, D, E, H, F. So I have a cycle. I hit every vertex, but I didn't hit every edge. I didn't draw the same shape. This doesn't quite work out. Got another one. Let's try this one. B, C, D, E, H. I've got another H, which I'm worried about because I don't know how to do two H's in a row. B, C, D, E, H. I'll just skip that H maybe. F, G, A, B, G, H, D, B. So this one looks like B, C, D, E, H, F, G, A, B, and now G, H, D, B, starting and ending at B. There we go. That looks good. All right, now I have the same shape. I've drawn everything. I never lifted up my Sharpie marker. I went from here all the way around and then finished it up. It looks like there are some other ones, so another one would be A, B, C, D, B, G, H, D, E, H, F, G, A. Also looks like it works. So, okay, we can do it there. Good. How about another one? Anybody else like play this game all the time when they were bored in class? I feel like I did this all the time. It's always on your mom's Facebook. Yeah, this is very much a mom Facebook type thing. Oh, I should give you a labeling. This one's a little shorter. A, B, C, D, E. Draw me that shape without lifting up your pencil. Get back where you started. I feel like this one was a favorite. I normally put the point up at the top, and then it was like a house. That's how I drew a house in like grade 2. All right, what do we got? We got here's my A, B, C, D, E. So suggestion is A, B, E, C, A, E, D, C, or maybe C, D. Let's see, where do we get from here? A, B, E, C, to A, to E, So I can't go back to C. So I got to go to D, and then C, and then B. So E, D, C, B. All right, did I do it? And by me, I mean, did Ashley do it? Shouldn't take credit for Ashley's work. But we didn't end up where we started. So I did draw the picture. I did get all the edges. But I started at A and I did end up at B. So partial points. But I didn't end up back where I started. Any thoughts? Is that maybe the best we can do? Oh, you wanted a correct answer. Well, joke's on you. You gave the best answer you could. Gonna give you a nice slick argument that what I asked you to do was impossible. On this graph, there is no way that you can start at A, end at A, and hit every edge exactly once. Yeah, Owen's got it in chat. Why is it? How am I going to justify that? How is it possible, or why is it that it's not possible to start at A, hit every edge, and end up back at A? Really simple. A has 3 edges coming out of it. If I start at A and I leave, I've got to hit those 2 other edges at some point. So I leave A, and at some other point, I come back to A on this edge. I have to leave A again on that edge, and now there's no way back. In order to hit all 3 edges, if I start at A, I leave, come back, leave. There's no way for me to end at A. And that's just because the number of edges incident to A, the degree of A, is odd. If the degree of A is odd, you can't start and end at A. It's important enough, I'm going to write it down. Then a circuit can't start and end at A. You can't start and end at A because the number of times you enter a vertex has to be equal to the number of times you leave a vertex in a circuit. If we go back to this example, how many times do I enter G? Well, I come in once and I leave once, and then I come in once and I come in a second time and I leave a second time. And if we look at my example, here's entering G and leaving G, and then here's entering G and leaving G. If you have an odd degree vertex, that can't happen. And because of the way circuits work, I start and end. Where do I start and end here? I start and end at B. If I wanted to start and end at H, and I know this one already, I've got a really easy way to do it. Just start at H. H, F, G, A, B, G, H, D, B. Work my way back around. C, D, E, finish at H. So if you have one of these circuits, if a degree A is odd, a circuit can't start and end at A if it hits every edge. I should add that. And in fact, if the degree of A is odd, it can't be on a circuit that hits every edge. Because any circuit that hits every edge, you can start and end wherever you want. Here I started and ended with B, but there's nothing special about B. I can just move along the circuit to wherever I want the start to be, and then I say now I'm starting at H, or now I'm starting at A, or now I'm starting at G, or now I'm starting at D. So in fact, oops, that's not how English works. In fact, a vertex with odd degree can't be on a circuit that hits every edge. So we have a name for these circuits. And this is one of those things where it's just named after somebody famous. So these are called Eulerian circuits, and they're named after Euler, whose name is spelled E-U-L-E-R. Looks like Euler, but this is pronounced Euler. And an Eulerian circuit is a circuit containing every edge. So what do we know about the existence of Eulerian circuits? Can an Eulerian circuit exist if any vertex in the graph has odd degree? No, right? This argument says if any vertex has odd degree, then you don't have a circuit. You don't have an Eulerian circuit. What is less clear, but is still true, is that if every vertex has even degree, you do have an Eulerian circuit. So here's our theorem. A graph has an Eulerian circuit. I'll give him a capital E. It's pretty famous. Eulerian circuit. If and only if every vertex has even degree. So if every vertex has even degree, like we saw in this example, degree 2, 4, 2, 4, 2, 4, 4, 2, then there must be an Eulerian circuit, and we found it here. But here, A has degree 3, we're already out of luck. We know that no Eulerian circuit is possible. What did we find, though? We were not able to find an Eulerian circuit, but we found something that had every edge. It did repeat vertices, but it didn't repeat edges. The longest trail in particular, we found an Eulerian trail. An Eulerian trail is an open trail containing every edge. So circuits are trails, but Eulerian circuits are not Eulerian trails. Eulerian trails in particular do not start and end at the same place. Eulerian trails have to be open. And the reason we make that restriction is we want the following theorem. A graph has an Eulerian trail if and only if. Okay, so let's stop and think for a second. What should go here? This vertex A that has odd degree stopped us from being able to do an Eulerian circuit, but it didn't stop us from being able to do an Eulerian trail. The thing about A was, since it had odd degree, you could leave it one more time than you could enter it. So leave, enter, leave. We ended at B. B also has odd degree. That means we could enter B one more time than we could leave it. Enter, leave, enter. Every other vertex has even degree. And that turns out to be exactly what we need. You have an Eulerian trail if and only if exactly two vertices have odd degree. So, now you know the trick to all your mom's Facebook puzzles. How do I make this? No, let's check the degree of E and C. 1, 2, 3, 4. 1, 2, 3, 4. The trick to finding an Eulerian trail is you always know you have to start at one of the vertices that has odd degree and end at the other one. So I know if I'm going to hit every edge, I need to start at A and end at B, or start at B and end at A. So, using this now, we can talk about some of our standard graphs and ask, do these have Eulerian circuits? Do these have Eulerian trails? Oh, one more thing I should say. If you have an Eulerian circuit, if a graph has an Eulerian circuit, it is called Eulerian. Not if it has a trail, just if it has a circuit. Yep, an open trail does not end on the same vertex it started on. But it covers all the edges, not all the vertices. Eulerian, we're worried about covering edges. Which, good way of remembering that. Put this off on the side. Eulerian cares about edges because they both start with E. Okay. Covering all the vertices is different. That's Hamiltonian. Okay, so a graph is Eulerian if it has an Eulerian circuit. So which of these graphs are Eulerian? We've got C7, P6, K4, K6, 8, and Q5. Okay, for each one of these, I have to figure out, does every vertex have even degree? So what does C7 look like? C7 is, right? C7 is a cycle with 7 vertices. 1, 2, 3, 4, 5, 6, 7. Heptagon, very nice. All the degrees are the same, all the degrees are 2. So in any cycle, all of my degrees are 2. 2 is even. So yes, I'm Eulerian. Okay, what about P6? P6 is no. P6 is a path on 6 vertices. 1, 2, 3, 4, 5, 6. And in a path, I've got a lot of vertices of degree 2 and then 2 vertices of degree 1. I'm not Eulerian because I don't have an Eulerian circuit. I do have an Eulerian trail. It's the obvious one. Okay, K4. My K stood for complete, because mathematicians don't know how to spell. The complete graph is the graph that has every possible edge in it. So I have 4 vertices, every possible edge. What are my degrees? Right. No, everything has degree 3. Not only am I not Eulerian, I don't even have an Eulerian circuit. There's no way to draw the box without the roof on top, without overlapping. Which is why, when I was in grade 2, I always used to do this. But I could never get the box without the top. I couldn't get back to that edge. Well, it's not possible. There's too many vertices of odd degree. Okay, K68. This is a complete bipartite graph. So here I've got 6 vertices. And here I've got 8 vertices. And then I've got all of the different edges between my 2 parts, A and B. I'm not going to draw in all those edges. There's too many edges for me to draw. But is it Eulerian? Yes. Okay, so if it's Eulerian, why? What are my degrees? Give me an argument. Everything over here has degree 8. Pick any vertex in A you want. I don't care which one. They're all adjacent to these 8 things and nothing else. So everybody over here has degree 8. And everybody over here is adjacent to everything in A. So I always have 6 edges coming out. Everything over here has degree 6. All 8s and 6s, everything is even. I don't know what the Eulerian circuit is, but I know that one of them exists. Right? All kinds of crazy bouncing back and forth. Okay, and that brings us to Q5, which I'm not even going to attempt to draw. How does Q5 work? At each vertex of Q5, I have a binary string with 5 bits in it. So maybe I have 1, 0, 0, 1, 1. And I'm adjacent to every other vertex that differs in one spot. So I've got 5 bits that I can change. So I'm adjacent to 0, 0, 0, 1, 1. I'm adjacent to 1, 1, 0, 1, 1. I'm adjacent to 1, 0, 1, 1, 1. I'm adjacent to 1, 0, 0, 0, 1. And I'm adjacent to 1, 0, 0, 1, 0. And that's going to be true for any vertex I pick. So what is the degree of any vertex in the 5-dimensional hypercube? 5. So is Q5 Eulerian? No. Bonus question, because I got 2 more minutes. How many edges are in Q5? How do we figure this one out? Definitely more than 5 edges in Q5. Because now think about this vertex. This vertex is also going to be adjacent to change any one bit. So this vertex is adjacent to 0, 0, 0, 1, 0, and other things. Can I explain why K68 is yes? So all of the vertices in A are adjacent to everything in B. So every vertex in A has degree 8, which is an even number. And all of the vertices in B are adjacent to everything in A. There are 6 things in A. So everything over here has degree 6. That's also an even number. So all of the degrees are even, and that's what we need to be Eulerian. Yeah, let's talk about Q5 some more. So Q5, how does Q5 work? Q5 is the hypercube on dimension 5. The way hypercubes work is you draw out this binary string, and you draw all possible binary strings. So first question, before we get to number of edges, how many vertices are in Q5? How many strings of zeros and ones with 5 numbers are there? 2 to the 5. Good. Good combinatorics question, right? Rule of product, 5 options, 2, 2, 2, 2, 2. 2 to the 5 is 32 vertices. Each vertex is adjacent to each other vertex if all you have to do is change one number. So here, I change the 1 to a 0. Here, I change the 0 to a 1. Here, I change the 0 to a 1. Here, I change the 1 to a 0. Here, I change the 1 to a 0. And those are the 5 things that I'm adjacent to. So if I want to figure out how many edges are in my graph, I have 32 vertices. Each has degree 5. And I have this thing called the handshaking lemma. This was also from Tuesday. The handshaking lemma says add up the degrees of all of your vertices, you'll get twice the number of edges. So this tells me that 2 times the number of edges is equal to 5 added up 32 times, so 32 times 5. Or the number of edges is equal to 16 times 5, which is 80. So I get 80 edges here. How do I calculate the 32? I want to know how many ways are there to write a 5-digit number where every digit is 0 or 1. So from my rule of product, I set up a 5-step process. Step 1, pick a 0 or 1 for the first place. Step 2, pick a 0 or 1 for the second place. Step 3, 0, 1. Step 4, 0, 1. Step 5, 0, 1. I've got 5 steps, each with 2 options. So 2 times 2 times 2 times 2 times 2. 2 to the 5th is 32. Okay, I've run a couple minutes over, so I'm going to stop there. I'll have office hours today if you want to talk about anything that we missed. Quiz 6 will be up this weekend, and test 3 coming out soon. Coming out on Monday. So thanks, everybody. See anyone who wants to hang out in office hours. Otherwise, see you next week. Have a good weekend.